Hey guys, today we'll be focusing on KSP and specifically how to determine the solubility given the solubility product constant. The solubility product constant, also known as KSP, is the equilibrium constant for a solid substance dissolving in an aqueous solution. For example, if we had table salt dissolving in water, it would produce a salt aqueous solution. Again, it represents the level at which a solute dissolves in a solution. If we consider this equation, here we have the compound lead iodide, which dissociates into its two ions, lead with a charge of +2 and iodine with a charge of -1. Now, how would we write the KSP expression for this equation? That answer can be solved by using KSP equals the concentration of the products to the power of X. Remember that KSP is the concentration of the products dissociated only. If we take this equation again, all you have to do is substitute the concentrations into the expression. So we have the concentration of lead multiplied by the concentration of iodine squared. The reason we have iodine squared is because in the balanced equation, there is a coefficient of 2. And this is a common mistake other students make all the time, is forgetting the coefficients. So if there are coefficients in front of any of the products, it is necessary to raise the product to that coefficient power. Note that the reactant is not included in the KSP equation, recalling that solids are not included when calculating equilibrium constant expressions because their concentrations don't change the expression and any changes in their concentrations are insignificant and therefore omitted. Okay, now moving on. Let's attempt the first example. So here it says, calculate the molar solubility for barium fluoride, BaF2, at 25 degrees Celsius. Generally, for these types of questions, the KSP will either be stated in the question or located somewhere in a table provided. In this case, we're lucky enough to have the table provided for us, and we can figure out the KSP value for BaF2, which is 1.7 times 10 to the negative 6. Now that we have that, we can go ahead and write out our balanced chemical equation, which is step number 1. It will look like BaF2, solid, remembering to include the states, dissociates into barium with a +2 charge, aqueous, and fluorine with a -1 charge, aqueous as well. Also, since we have 2 fluorines on the left side, we have to add 2 on the right side to make sure the whole equation is balanced. After that's done, the next step is to write out the solubility product expression by substituting in the ions barium and fluorine. So that will look like the concentration of barium multiplied by the concentration of fluorine to the power of 2. Again, we have the 2 here because of the coefficient of 2 in our balanced chemical equation. After figuring out our equation, we can set up an ice table to organize our information. We make sure to disregard the first column because we don't include reactants in our equilibrium expression, and we know that the initial values of our products are always 0, the change in barium is just X, and the change in fluorine is 2X, remembering that we have a power of 2 in our expression. Now we just add everything together. 0 plus X gives us X, and 0 plus 2X gives us 2X. The final step is just to substitute the values from the last column of the ice table into our expression and solve for X. So we have X multiplied by 2X to the power of 2, and we do exponents first, so that would give us 4X squared multiplied by X again. And then we input the value of our KSP into the equation, which is 1.7 times 10 to the negative 6, and we isolate for X, so we divide both sides by 4, and that would give us X cubed equals 4.3 times 10 to the negative 7. And now we cube root both sides, which would give us X equals 7.5 times 10 to the negative 3. Therefore, the molar solubility of barium fluoride is 7.5 times 10 to the negative 3 moles per liter. And there we go. I hope you learned how to easily determine the molar solubility of a compound given the solubility product constant, and good luck.